Hi, it's Mr. Duffy. Welcome to chemistry. Today we're going to continue our unit on the development of the atomic theory. In our last lesson, we talked about John Dalton's first atomic theory that was developed and based on evidence. In that theory, he talked about how atoms are the smallest unit of matter. Today we're going to be talking about a lesson of actually particles that are smaller than an atom, the protons, the neutrons, and the electrons, and we're going to talk about how those particles were discovered. So let's go ahead and get started. So after John Dalton discovered or proposed his first atomic theory, a lot of scientists began to wonder, again, what atoms were like. What was the structure? Was an atom just a solid sphere with no internal structure, just again a big solid ball, or was it made up of smaller little things that were again maybe moving around on the inside? What was it like? And this actually didn't happen right away. It took about 100 years for scientists to start developing and trying to understand what these smaller particles were. Today, we're going to talk about three of the scientists that did some work and discovered these new subatomic particles. But I want you to be clear that there were actually a lot of scientists that made significant breakthroughs. And this slide here proposes and shows you some of the significant discoveries in our understanding of the atomic theory. So let's talk about one of these discoveries. Was the first discovery of particles that were something other than atoms was the discovery of radioactivity. Radioactivity was discovered in 1896, and basically what it amounts to is it's rays or particles that are given off by unstable nuclei. There are three main types of radiation: alpha rays, beta particles, and gamma rays. Now, we'll talk about these a little bit more in a future lesson, but again, what was discovered about these was the fact that these were not elements, they were not atoms, they were something different. They were discovered by Henry Becquerel, and he discovered them that these particles could actually expose photographic film. Later work to explain what radioactivity actually was done by some very famous people, the Curies, Marie Curie and Fran- uh, Francis, I believe Francis Curie, were two of the scientists that did the leading research on radioactivity. Um, Marie Curie is one of the most famous women scientists in history. But again, radioactivity is not a subatomic particle, not something that makes up the atom. And so it actually took another invention to discover the first subatomic particle. This invention was called what's called the Crookes tube, or sometimes it's called a cathode ray tube. And basically, it's a glass tube where electricity can run through it, and what it does is it glows, creates a glow. Now, we actually, what's interesting is this is a somewhat of a invention that it still sticks around today, or at least for the last few decades or so. But it actually is a device that could have been found in color televisions or televisions. They used to have ray tubes in them as well, where beams of red light or blue light or green light would be bent by a magnet and sent to hit a dot on a television or a pixel, basically. And then that would form the images you would see on TV. So this invention from 200 years ago, a little bit less than 200 years ago, still is around in some very old televisions and so forth. More modern televisions, LED televisions and stuff, do not use this technology, but older televisions do. So this invention, again, the Crookes tube, was used by a man named J.J. Thomson, and he was an English physicist in 1897, and he used it to discover the first subatomic particle. Let's look at his invention or his discovery. So in Thomson's experiment, he took the cathode ray tube and ran electricity through it. When he ran electricity through it, again, it gave off a glow, a beam of particles that were able to travel from the negative end of the cathode ray tube into the positive end. Um, again, he could measure them and see their movement from the negative end to the positive end, and they again glowed. When he turned them off, when he stopped the electric current, they disappeared. So then he decided, okay, well, what if I take a magnetic field and put it around the tube? What's going to happen to these particles? And what he'd noticed is when he turned on the voltage source that they actually bent. So they bent away from the negative end of the magnet and towards the positive end. This was interesting. What is this telling, J.J. Thomson at this point in time is basically that these particles must be negatively charged. And the reason why, again, that would be the case is because if we remember opposites attract, a positive charge and a negative charge, they attract to each other, and like charges repel each other. So you could tell again that this was definitely some type of negatively charged particle because it was going away from the negative end and towards the positive, attracting to the positive end. This was definitely something negative. But it doesn't tell us the size of the particle. So it does tell us again that it's a negatively charged particle. It's going to bend towards the positive end. But is it smaller than an atom? We need to figure that out. And so he has to do a few more sets of experiments, something more advanced than just, again, measuring um, that it bends. He has to take some measurements of how much it bends. And so we're not going to go into the math behind it, but there is a math. He can measure again how much charge he applied to a magnetic field, and then how much the beams moved from their original position, and do some math to actually do the calculation. But what he ended up finding was that these particles are very, very, very small. They're about 1/1000th the size of a hydrogen um, mass, and hydrogen was the lightest element known at that point in time. So they are extremely, extremely light. They're negatively charged. He found that out again by just them going towards the positive end, and they are extremely light. So that must mean that this particle is smaller than an atom, and all atoms must contain them. All atoms must have these negatively charged particles. He knows that all atoms must contain these negatively charged particles because he used multiple different types of metal and gases inside that tube to come to that conclusion. And he found the same results no matter what he did. So, this is a significant breakthrough in our understanding of an atom. We know that atoms now have negatively charged particles that they contain. He also knew, though, that atoms are not negatively charged. And so that paves the way for somebody then to discover what the positive charge is in an atom. So he knows that there is this negatively charged particle in an atom, but there also must be a positive charge. He does not discover that, but again, he paves the way for someone else. What he does do is, well, actually, some another man by the same name of Thomson. His name was actually William Thomson, or he was given the name Lord Kelvin. But this guy comes up with the Thomson model of the atom, also sometimes called the plum pudding model. And we'll talk about why that's the case. But again, it's not the same Thomson. J.J. Thomson did discover the electron, and William Thomson's the one that came up with the plum pudding model. But basically, again, knowing that there are these electrons and that atoms are neutrally charged, then there must be some positive region, positive area surrounding these electrons. And so William Thomson described this as the atom as a plum pudding. Plum pudding back in the time was a common dessert with little raisins spread out in a bread pudding. And the electrons were evenly dispersed throughout this positive charge. And this is what they believed the atom looked like in the early 1900s. Now, the plum pudding model is not what we think of today as what an atom looks like. So it takes another scientist to actually come in and find the better structure of what an atom looks like what we think of it looks like today. And that is the development of what we call the Rutherford model of the atom. It's the modern view developed by a man named Ernest Rutherford. Ernest Rutherford, actually, interestingly enough, actually was a student of J.J. Thomson. So um, he learned physics in J.J. Thomson's lab. J.J. Thomson again discovered the electron, and his student, Ernest Rutherford, comes and actually finds the nucleus um, later on, developing, again, the more modern version of what we think of as the atom. So one of the things that led him to this discovery was his work with some radioactive particles called alpha particles. And what he noticed was that sometimes these alpha particles were deflected by something in the air. He would, again, just have them pass through the air, and then he was having them hit photographic film, and sometimes they bounced and hit something in the air and ended up exposing the film in areas where he didn't think that was going to be the case. And so he did what's called the gold foil experiment. Instead of using air, he took a more dense atom, a more dense material than air, and had those alpha particles run through the gold foil. A very, very thin piece of gold foil, but again, gold foil nonetheless. Here's a setup of his experiment. Basically, again, he needed a source of those alpha particles, and alpha particles are made from radioactive materials, and he used a source of polonium. Polonium was a newly discovered radioactive material, again, discovered by Marie Curie during that time period. And he encapsulated it in a lead container with a very small opening, in which case the alpha particles would be able to be shot out of the opening towards the gold foil. And then as they were shot out towards the gold foil, they would again hit the gold foil, and he would measure where the alpha particles were hitting with a fluorescent screen or a photographic film, basically, that surrounded the gold foil, and he could make his measurements based on that. Now, I think that's actually important for me to kind of show. I have a simulation of this that I can show you versus um, going through some slides. So I'm going to go away from this slideshow to kind of take a look at this simulation. What we have, according to this simulation, is I have a setup of the gold foil experiment according to the plum pudding or J.J. Thomson, the Thomson model of an atom. We have small little dots, and those are our electrons, surrounded by a cloud of positive charge. And if I allow those alpha particles to go through the atom per se, we notice that basically, again, they go through and they basically go straight through without hitting anything. Alpha particles are extremely heavy in comparison to the small mass of the electron. So basically, what would end up happening is if the alpha particles did hit the electron would just have to move out of the way. And that's, again, basically what the prediction was that was going to happen, according to, again, our current model of the atom back in the early 1900s. But that is not what ended up happening. What ended up happening was some of those alpha particles bounced off. That must have meant that they were hitting something. And what Ernest Rutherford took from that experiment was that most of these alpha particles, are actually going straight through. But again, some of them are bouncing and some of them are hitting something in the gold foil. And what is that something? Well, what he ended up concluding, though, was that it's a very dense region in the gold foil, and he called it the nucleus of the atom. So, two main takeaways from his experiment were that the atoms are mostly empty space because most of the alpha particles went straight through, but there is a very dense central core to an atom because some of these alpha particles hit that dense central core and bounced off of them. That leaves, again, well, the fact again that there is the proton. It is hypothesized at this point in time because that's what must give the nucleus its positive charge. But after that point in time, the only thing left to be discovered really was the neutron. The man that discovers the neutron is a guy named James Chadwick, and he again is kind of working with radioactive materials. And what he was taking a beryllium atom and bombarding it with an alpha particle. And what actually happens is the alpha particle combines with the beryllium atom and makes a carbon atom. This is a process called transmutation. You might say, Mr. Duffy, didn't you just talk about transmutation in one of our earlier lessons when we talked about alchemy? And transmutation is not possible. That's where they were trying to change lead into gold. And that's actually correct. Transmutation is not possible by normal chemical reactions. But nuclear reactions, in which case we're changing the nucleus of the atom, again, by using radioactive materials, that actually is a possibility. So it is possible to change one atom into another using a nuclear reaction. And that's what James Chadwick did. Again, he took an alpha particle, bombarded a beryllium atom with that alpha particle. It mutated into carbon 12, but that left a little neutron left over. And that neutron that was left over, he was able to measure the difference in mass between my reactants and my products. And according to the law of conservation of mass, mass cannot be created or destroyed. So he knew that that remaining mass must have been a neutron, a particle of similar mass to a proton, but with neutral charge, no charge. And so that leaves us with all three particles of an atom, all three subatomic particles discovered. We have our, again, protons and neutrons in the nucleus. We have our electrons around the outside. And again, we have discovered the nucleus is the very dense central core of an atom. And that's all thanks to, again, J.J. Thomson, Ernest Rutherford, and James Chadwick. So hopefully you understand a little bit more about how the subatomic particles were discovered and how they are arranged in an atom. And thank you for watching.